and fluidized beds. This is your 17th class on transport phenomena. In this class, we will study the packed and fluidized beds. As an introduction, let us take the example of some of the gas-solid reactions. Gas-solid reactions. The important gas-solid reactions of metallurgical importance are: first is the roasting of metal sulfide, that is, it is called roasting of metal sulfide. Another important reaction is, once you have obtained the ZNO through the roasting of the zinc ore, that is the sphalerite, you will obtain zinc oxide, and this is subjected to reduction with carbon in an imperial smelting furnace, imperial smelting blast furnace. So, the reaction takes place in this manner: Zn plus CO. Another example is reduction of hematite by carbon monoxide in blast furnace. In all these reactions, you will find that there is a solid, there is a gas, solid gas. Sorry, this is another example. You should remove it. Another example is, this is solid, this is gas. So, this is called your reduction of metal oxide, reduction of metal oxide. This example corresponds to reduction of metal oxide. These reactions are, such reactions are executed successfully through packed and fluidized beds, bed processes classified as, such packed bed processes as well as fluidized bed processes can be classified as: number 1, that is called fixed bed process, fixed bed processes. Fixed bed operations are processes are batch operations. The nature of such processes are batch processes or batch operations. That means you are putting the raw material in the process and you will go obtain the product. Again, for the second round, you have to charge the raw material and you will get the product. So, in every batch there is a reactant, there is a product. So, these are the batch operations. Also, no movement of solids, no movement of solids with respect to each other or with respect to walls of the reactor. So, these are called the fixed bed processes. Number 2 are the moving bed processes, in such processes solids are conveyed through the reaction zone either under gravity example is the blast furnace, or driven mechanically. This driven mechanically you can easily see in the sinter machine. Sinter bed, in processes like rotary kiln process, either the rotary kiln process for the cement making or the rotary kiln process for the production of sponge iron, both the mechanism can be seen. Both the mechanism can be observed. Number 3 is the fluidized bed process, also known as pneumatic processes. Bed of finely divided solids or is agitated and lifted by a rising gas or liquid stream. So, this is the classification of such packed and fluidized bed, or the beds which are generally used for the execution of gas solid reactions, either it is of the metallurgical concern or even in the petroleum industry. The catalytic cracking of the petroleum is being executed by such type of processes. Because of the fact, in the case of highly exothermic reactions or endothermic reaction, the temperature of the process can be maintained with up to a larger extent of uniformity if you are using such type of processes. This is the beauty of these processes over the conventional processes of either catalytic cracking or the roasting or the reduction of metal oxides. So, the next thing is the characteristic of packed bed. In your lab classes of this particular subject, you have to conduct the first and second experiment related with the packed and fluidized bed, in which the thing that I am going to teach you people is of immense importance. So, characteristics of packed beds. packed bed can be characterized by the parameters related with flow of fluids through packed bed or through it, you see, through it. Okay. The various parameters are prior to the discussion of the various parameters associated with the flow of the fluid to any packed bed, let us take the reference of a figure which is a schematic diagram for the packed bed. Let us suppose these are the bed particles. So, there are the void space among them, definitely due to the spherical approximate spherical symmetry, there must be some sort of void edge through it. This is your gas flow, this is your schematic packed bed. So, the various parameters are number A, the void edge and particle characteristics, Let us consider a packed bed schematically shown in the figure. Schematically shown in the figure. The bed is composed of uniform sized particles and particles filled in a vertical cylindrical tube, Okay. Such a bed can be characterized through the parameters number 1. First is the void edge, or this is also called the void fraction. This is denoted as a letter epsilon. This is defined as epsilon, that is the voidage, that should be equal to total volume of bed minus total volume of solid particles divided by total volume of bed. Let us suppose the total volume of bed is Vb, total volume of solid particle is Vs divided by Vb, that is equal to 1 minus Vs by Vb. So, the Vs can be given as 1 minus epsilon into Vb. So, this is the expression which can be used to characterize this packed bed. So, this is one parameter. Then another parameter is particle size and shape. Particle size and shape. Every particle present in the packed bed may not have a spherical shape, and there is possibility of beds having mixed nature of particle size and shape. To take care of it, a parameter called volume equivalent parameter, very important parameter it is, that is called the volume equivalent parameter. This is denoted by letter dp, is used for describing the size of non-spherical particles. The question arises, how this quantity dp can be defined? This should be another question, because many times you have to describe the size of non-spherical particles. So, this dp defined as dp is equivalent to diameter of a sphere having volume equal to that of particles. So, if V is the volume of the particle, that should be equated to 4 by 3 pi dp cube, from where you can easily determine the value of dp. So, let it be question number 1. This definition is regarded as equation number 2. Next is the particle shape factor. Third one is the particle shape factor. Next thing is the particle shape factor. Particle shape factor, this is abbreviated by letter phi s, phi suffix s. Through the experimental determination of mesh size, by sieve analysis experiment, it can be concluded. Basically, what is done in the sieve analysis? You take the different sieve size and a vibratory motion is being given to that, to the sieve shaker. Let us assume you have to study the grain size distribution in a river sand. Then you take some amount of river sand, putting up the upper pan, give a vibratory motion, and then after some time you have to calculate the quantity of the sand particles retained on the various sieves, from where you determine the grain fineness number, an important quantity for the foundry application, GFN. This GFN determination is itself based on the fact that an approximate spherical symmetry is being executed by each and every particle irrespective of its shape and size. I am not saying that a perfect spherical symmetry is being obtained, but an approximate spherical symmetry can be assumed to be there in each and every case. This fact is attributed to this experiment, that is the determination of mesh size by the normal sieve analysis experiment. So, it can be concluded that an approximate spherical symmetry is being maintained by irregular shape particles. To quantify the deviation of a particle shape from normal spherical shape, a quantity called shape factor, also called a Leba shape factor, a quantity called shape factor is used. This is defined as this phi s, In the foundry, the angular strengths are used, but by utilizing the Lewis shape factor, that those particles may be regarded as the spherical particles. So, this phi s is defined as surface area of sphere of equal volume to particles. That means the volume of the particle that should be equated to the volume of the sphere. We will go obtain the dp value. 4 pi dp square is the surface area of the sphere of equal volume to particle divided by surface area of particles. Surface area of particles. So, phi s is less than 1 for non-spherical particles, and phi s is equal to 1 for the spherical particles. Spherical particles, this is for the non-spherical particles. Non-spherical particle, but however this should not be utilized as a normal abbreviation. For spherical particles phi s is equal to 1. Another packing material which is utilized in our laboratory in the transport phenomena, that is the bird saddle, the value of phi s is 0.30. So far as angular sand particles are concerned, this has a very high value of the deviation, that is equal to 0.73. Now, if phi s, dp and epsilon all are known, then another factor, a characteristic factor you can say, which can be extracted through this quantity, is the specific surface area, that is the area per unit volume. Specific surface area per unit volume of bed may be evaluated if phi s, dp, epsilon are known by using the equation, by using the relationship as the specific surface area A, that is equal to 6 into 1 minus epsilon, 6 into 1 minus epsilon divided by phi s dp. Let it be question number 3. Let it be question number 4, sorry. Let it be question number 4, let it be question number 3. Another important thing is the pressure drop. That means, what is the pressure drop which is there in a packed bed or in a fluidized bed? So, the next thing is the pressure drop. Next thing is the pressure drop in packed bed. Pressure drop in packed bed. This is the another characteristic term, that is the pressure drop in packed bed. For this, Argon equation is used. This equation is based on the following assumptions. The assumptions are following assumptions. Number 1, number A, gravity effect or effect is neglected. Gravity effect is neglected for horizontal bed, for a horizontal bed or a small bed length. This is the first assumption that this Argon equation has. Number 2, particles form uniform packing. So, it means a continuous flow channel forms. That means channel forms through which the flow of the gas can be executed. So, continuous flow channel forms. Number C, beds can be modeled as a bundle of small pipes. There will be small channel will form. So, those channels may be regarded as they are the smaller pipes throughout the entire bed. So, bundle of small pipes. And next assumption is flow is laminar. That means friction factor that is equal to a constant divided by Reynolds number. So, on the basis of these 4 assumptions, Argon developed an equation which is responsible for the calculation of pressure drop in the packed and fluidized bed, and the equation is Argon equation is nothing but it is the equation which expresses pressure drop as a function of gas flow through packed bed. Basically, this Argon equation is given as G C, where the G C is the conversion factor. In magnitude, it is generally equal to the acceleration due to gravity, such as 32.2 foot-pounders per unit force. So, that we have to utilize the conversion factor, but basically in magnitude it is equal to the G value, because the value of G in the FPS system is 32.2 feet per second square. So, this is the G C into delta P by L, that is equal to 150 1 minus epsilon whole square divided by epsilon cube mu V naught divided by phi s dp square whole square plus 1.75 1 minus epsilon by epsilon cube into rho g into v naught square divided by phi s dp. Let it be question number 5. Delta P here, delta P is the pressure drop across length L, across length L. Phi s dp you are knowing, epsilon you are knowing, mu. L is the bed length, mu is the viscosity of gas, mu is the viscosity of gas, and this v naught, that is called the superficial velocity, and it is defined as, v naught is equal to volumetric flow rate. This is defined as volumetric flow rate divided by cross sectional area of bed, This equation number 5 can be rewritten as, GC delta P by L, that may be written as 150 1 minus epsilon whole square divided by epsilon cube phi s dp whole square into mu v naught plus 1.75 into 1 minus epsilon divided by epsilon cube into this rho g को भी इधर रख लो, into epsilon cube into phi s into dp v naught square, और GC delta P by delta, here you should also write the GC, that is the conversion factor. Let us take the example of FES 32.2 poundal LB force raised to the power minus 1, foot poundal force raised to the power minus 1, that is the conversion factor. So, the GC delta P by L, that is equal to K1 mu V naught plus K2 V naught square. Here K1 and K2 are constants, and that will be a function of gas flow rate, This quantity K1 mu V naught, this is a term corresponding to laminar flow through the capillaries, Okay. So far this term is concerned K2 V naught square, K2 V naught square. This is a term corresponding to presence of turbulent region at high flow rate. Both these equations 5 and 6, both these equations 5 and 6 can be used to evaluate the pressure drop through the pressure drop, that is the PD, through the bed. In the experiment, that is with reference to experiment number 1 of our class, you will find that there is a large number of variation in the delta P by L value obtained and the delta P by L value as experimentally determined. This is basically due to the reason if you have done some mistakes, or that is not the mistakes which you have executed in a known manner, but unknowingly it happens that the correct assessment of the use of this term K1 mu V naught and K2 V naught square is generally cannot be assessed through the simple experimental techniques that we have in the laboratory. So, after the graphical analysis, you can easily assess that how much deviation is there, and the basic reason which stands responsible for the interpretation of the large variation in the delta P by L value experimental and delta P by L value theoretical is the incorrect assessment of these two terms in order to evaluate the value of delta P by L value as per equation number 5 of the 6. Thank you.